In today's video, we will talk about methods of point estimation. The basic goal would be to introduce two methods. The first method would be the method of moments, and the second method would be a more widespread technique, which is known as the maximum likelihood estimation. Let's begin by setting up some basic machinery here. So suppose we have a population that has distribution X and its BMF or probability density function of X is given by the function f of X. In this setting, we will let x1 through xn be a random sample of size n coming from the given population. Then for k equals 1, 2, 3, all the way up to infinity, the kth population moment or the kth distribution moment for the density function fx is the expected value of the random variable x to the power k. You can write it as e of x to the k. The kth sample moment for the random sample x1, x2 up through xn is the average of the kth powers, sum of the kth powers of the sample elements, that is x1 to the k plus x2 to the k all the way up to xn to the k divided by n. The method of moments uses these two moments, the population moments and sample moments, as follows. If there are m parameters, theta 1, theta 2 up through theta m, that we want to estimate using a random sample x1, x2 up through xn, we are going to get m equations by equating the first m population moments to the first m sample moments. And after that, we just pray that we can solve these equations to get our estimators for the parameters theta 1, theta 2 up through theta m, which we call theta 1 hat, theta 2 hat, theta 3 hat, all the way up to theta n hat. This method can be best understood by working out some examples. So let's work out when we are dealing with a sample coming from the exponential distribution. So suppose we have a bunch of random variables, x1, x2 up through xn, uh, a random sample coming from the exponential distribution with parameter lambda. Then in this context, we know that we only have one parameter to estimate, that is lambda. So we will only need to calculate the first moments, that is the first population moment and the first sample moment. The first population moment is the expected value of x, which equals 1 over lambda. This is a fact we know about the exponential distribution. And the first sample moment is 1 over n times summation xi. This is the sample mean. Now, following the process for method of moments, we will be equating the population moments to the sample moments. In this context, that gives us 1 over lambda, which was the first population moment, to equal the first sample moment, that is x bar, which solves for lambda equals 1 over x bar. This gives us that the method of moments estimator for lambda in this context is lambda hat equal to 1 over x bar. We next work the example where our sample is coming from a normal distribution. This is to say that we have n random variables, x1, x2 up through xn, and each of these are coming from the normal distribution with mean mu and variance sigma squared. We want to use this random sample to estimate mu and sigma squared. So in this context, k equals 2. We can calculate the kth population moments as follows. When k equals 1, we have the expected value of x, which exactly equals mu. When k equals 2, we want to calculate the expected value of x squared. Recall the awesome identity that the variance of x equals the expected value of x squared minus the square of the expected value of x. If we solve this, we get that the expected value of x squared equals sigma squared plus mu squared. If we equate the population moments to the sample moments now, we get that the expected value of x, that is mu, would have to equal x bar, which is the first sample moment, and we would have the second population moment, that is expected value of x squared, to equal summation xi squared divided by n. In this setting, the moment estimators are exactly given by the following equations. Mu hat equals x bar and sigma squared hat equals the following equation. We will next work with the gamma distribution. Assume that our sample, random sample x1, x2 up through xn is coming from a gamma distribution with parameters alpha and beta. That is, alpha is the shape parameter and beta is the scale parameter. In this setting, recall that the expected value is given as alpha times beta and the variance equals alpha times beta squared. So if we use our awesome identity from earlier, we notice that the second population moment exactly equals alpha times beta squared plus expected value of x squared. We get that the population moments are the first population moment equaling alpha times beta, and the second population moment equals alpha times beta squared times 1 plus alpha. Now, if we equate the sample moments to the population moments, we get the following pair of equations. We get x bar equals alpha times beta, and we get summation xi squared divided by n equals alpha beta squared times 1 plus alpha. We can solve this equation by setting a to be x bar and b equals the second sample moment, and we want to solve for alpha and beta the following equations, that is a equals alpha times beta and b equals alpha beta squared times 1 plus alpha. Notice that we will get beta equals a divided by alpha, and now we can plug this into the second equation and follow through the calculations to arrive at the value of alpha, which will be equal to a squared divided by b minus a squared. So therefore, the method of moments estimators for the gamma distribution are given by alpha hat equals x bar squared divided by 1 over n times summation xi squared minus the square of x bar squared, and beta hat equals x bar divided by alpha hat. We will now move to the next technique of estimation, which is the maximum likelihood estimation procedure. Uh, Suppose we have a random sample x1, x2 up through xn. This random sample is coming from a population with either the PDF or the PMF equaling fx. In this setting, we will let fx1, x2 up through xn be the joint PMF or the joint PDF of the group of random variables x1 through xn. Since the xi's are independent, notice that the joint PMF is going to be the product of the PMFs of each individual xi's, and we have misused the terminology here where we are denoting both the PMFs by the same symbol, that is F. Now, given sample data, small x1, x2 up through xn, we want to use these data points to estimate parameters theta 1, theta 2 up to theta m of the population. To do this, we will define the likelihood function for the sample data x1, x2 up through xn. This is going to be the function that is going to be depending on the xi's and the theta j's. The xi is going from 1 through n and the theta j is going from 1 through m. Notice that in this definition, the xi's are fixed, and this function really depends on the theta i's. The theta i's are allowed to vary over the parameter space. Uh, the likelihood function is a function of the parameters theta 1, theta 2 up through theta n, given a fixed sample data x1, x2 up through xn. Um, the maximum likelihood estimation principle uh, does the following. It finds choices of parameters theta 1 hat, theta 2 hat up to theta m hat, which maximize the likelihood function for the observed sample data, that is x1, x2 up through xn. So we're going to maximize over the parameter space for fixed sample data. This is to say that we want to find theta 1 hat, theta 2 hat up to theta m hat, such that the function fx1, x2, xn semicolon theta 1 hat, theta 2 hat up to theta m hat is greater than equal to fx1, x2, xn semicolon theta 1, theta 2 up to theta m for all possible values of theta 1, theta 2 up through theta m. It should have been theta m in the video. So the theta 1, theta 2 hat up to theta m hat will be called the maximum likelihood estimates or MLEs for theta 1, theta 2, theta m respectively using the sample data x1 through xn. And if we substitute capital Xi for small xi in these estimates, we will get estimators. Theta 1 hat, theta 2 hat up to theta m hat, which we will call the maximum likelihood estimators or MLEs for theta 1, theta 2 up through theta m respectively. Let's work out some examples. Suppose we are sampling from the exponential distribution. That is to say that we have x1, x2 up through xn, random variables coming from the exponential distribution with parameter lambda. In this context, the PDF of the xi's is going to be defined as fxi, comma, lambda, which will be equal to lambda times e to the minus lambda xi. The likelihood function is defined as the product of I going from 1 through n of fxi semicolon lambda. If we work through this calculation, you notice that we will get the likelihood function fx1, x2, x3 up to xn semicolon lambda to equal lambda to the n times exponential of minus lambda times summation xi. We want to maximize this as a function of the lambdas. So if we set g lambda to be equal to lambda to the n exponential of minus lambda times summation xi, we can take the logarithm of g lambda, and this results in n times ln of lambda minus lambda times summation xi. This is sometimes also called the log likelihood function. And as you can see, it's much easier to maximize than the original likelihood function g lambda. Now, if we set h lambda to be ln of g lambda, we can take the derivative of lambda. We are using the second derivative rule to maximize h lambda. We get the following derivative, and if we set the derivative to 0, you notice that the critical value is going to be given by lambda equals 1 over n times summation xi. You can also check that the second derivative of h lambda is going to be negative n over lambda squared, which is always negative, which tells us using the second derivative test that lambda equals 1 over n times summation xi is going to be a point of local maxima. Since the logarithm is an increasing function and lambda equals 1 over n times summation xi inverse maximizing h lambda implies that the same lambda is going to maximize our original likelihood function, that is g lambda. We can, as a result, conclude that the maximum likelihood estimate for lambda is going to be lambda hat equals 1 over x bar. Note that this is the same as the moment estimator for lambda that we got from our earlier calculation. Now suppose that we are sampling from the normal distribution, which means that we have random variables x1, x2 up through xn, a random sample coming from the normal distribution with parameters mu and sigma squared. In this context, our xi's are going to have PDF fxi, comma mu, comma sigma squared, given by the following formula. And the likelihood function can be calculated because of the independence of the random variables as the product of each of these PDFs, that is 1 over square root of 2 pi times sigma, the whole to the power of n, times the following exponent. We can now take the logarithm of this function to get the log likelihood function, which is going to be much simpler to work with. The log likelihood function in this case is defined as 1 over n over 2 times ln of 1 over 2 pi times sigma squared minus 1 over 2 sigma squared times the sum of xi minus mu, the whole squared. In this context, the log likelihood function is given as h mu comma sigma squared, and it's exactly the following formula. We now need to maximize the log likelihood function, h mu comma sigma squared. To do this, we will have to calculate the critical values of h mu comma sigma squared. That is, we'll have to calculate the derivative with respect to mu, the derivative with respect to sigma squared, and equate them both to 0 and work out these equations. We will then use the Hessian matrix to show that these critical values are in fact points of local maxima. We can do all of these calculations and show that the MLEs for the normal distribution are given by mu hat equals x bar and sigma squared hat equals 1 over n times summation xi minus x bar, the whole squared. Notice that the principle of maximal likelihood estimation gave us an unbiased estimate for mu, whereas a biased estimate for the variance. We will wrap up this video by talking about two important properties of maximum likelihood estimates. The first being the invariance principle, which says that if we have theta 1 hat, theta 2 hat up to theta m hat, MLEs for theta 1, theta 2 up to theta m, then h applied to theta 1 hat, comma theta 2 hat up to theta m hat will be an MLE for h applied to theta 1, theta 2 up to theta m. This is saying that calculating the MLE for a function of parameters is the same as calculating the function of the individual MLEs that you have calculated for theta 1 up to theta m. The second property is what is known as the large sample behavior of MLEs, which says that if your sample size is large, then the MLE theta hat for theta is at least approximately unbiased. That is to say that the expected value of theta hat is almost equal to theta. And it also has variance that is either small as or nearly as small as can be achieved by any possible estimator. To rephrase this, what it means is that the MLE theta hat is at least approximately or exactly the minimum variance unbiased estimator for theta. To summarize this video, we have introduced two techniques. We have done a bunch of examples. The two important techniques over here are the method of moments and maximum likelihood estimation. Both of these are techniques to find estimates for population parameters. We will talk a lot about these in future videos, but this is all for now. Take care of yourselves, and I will see you around.